Yesterday, we had been discussing efficiency and voltage regulation. We derived the condition for maximum efficiency of a transformer. This essentially allowed us to differentiate between distribution transformer and power transformer. Just to reiterate, the power transformer normally has maximum efficiency at 100% load condition or rated load condition. Under that condition, we will have basically the copper loss equal to constant loss, which means the constant loss, if we say that is 100 watts, the same 100 watts is going to be the loss under copper loss condition under full load when the transformer is carrying its rated current. So that is the characteristic of a power transformer or a transformer which is connected to a generator in the power station. Whereas distribution transformer normally has maximum efficiency corresponding to whatever is the prevalent load for the maximum portion of the daytime, or in a particular 24-hour period, whatever is the maximum amount of load that is being present for more amount of time, corresponding to that we will choose a distribution transformer which will have the maximum efficiency corresponding to that particular load condition. Right? We'll try to work out probably one problem for a transformer, but that I will do after discussing auto transformer. Okay? So the next topic that we are going to discuss is auto transformer. Okay? In the auto transformer, what is the major difference between an auto transformer and a normal two-winding transformer? Auto transformer actually is a single winding transformer. So I am not going to have two windings in this transformer. It will be a single winding transformer, which actually is very, very similar to a rheostat, but it is a non-lossy rheostat or potential divider. So it is really similar to a potential divider. But this is non-lossy. There is no loss. That means there is no resistance loss in this particular, apparatus. So what we are actually looking at is maybe to step up or step down the voltage or obtain an output voltage which is slightly different from the input voltage. Most of the times what we use the auto transformer for is if I am applying 220 volts, I may require a voltage as 230 or I may require a voltage as 200 at the output. And I want to make sure that very close to the input I am going to obtain the output, but I will be able to make fine adjustments by actually moving the jockey point. So let us say this is my auto transformer, which is a single winding transformer, and let's say I am applying 220 volts AC single phase here. Right? What I want is probably 210 volts. Then I may leave out only a few turns on the primary side. The secondary side will consist of, a little fewer turns as compared to the primary side. So if I may call this complete number of turns as N1 and I may have this as N2, the number of turns as N2. So what I get as the output will be less than 220 volts, slightly less than 220 volts. So I would be able to adjust the output voltage anywhere close to 220 volts. This is one of the major applications of auto transformer. It works like a potential divider. Most of the times, if I try to look at N1 by N2, it will be close to unity. Most of the times that is the way it will be. If I try to look at what is N1 by N2, it will be close to unity. But rather than using single winding, rather two winding transformers which are having a turns ratio 1:1, I am trying to use only one single transformer. The major advantage is the amount of copper used is minimized drastically. If I had been using two windings, I would be spending same amount of copper on either of the windings. Whereas here, one single winding I am utilizing, so obviously I am not really spending twice the amount of copper like what I would have done in the case of a two winding transformer. So the major advantage is saving on copper. And if I am having saving on copper, obviously if I am looking at the resistance of the primary winding and resistance of the secondary winding, I would have twice the I square R losses in a two winding transformer as compared to what I would get in an auto transformer. So I would say step up action is done quite easily, that is one thing. And advantages, if I try to look at it, we can say less copper utilization, right? And another thing is less losses. Clearly, yeah. It can be step up or step down. If I am applying the voltage until here, and if I try to take the voltage from here, it will be step up. So it can be step up or step down, depending upon to how many turns I am actually applying the voltage, and out of this, whether I am taking the same number of turns as the input at the output, or more number of turns or less number of turns. So it can be step up, step down, or just the transformation ratio being unity. Either any one of the options can be chosen, not a problem. So the advantages we said already. Definitely there should be disadvantages, otherwise we will not be using two winding transformer at all. So the major disadvantage of an auto transformer is no isolation. There is no isolation at all between the primary and secondary. I am going to have essentially electrically both of them are connected, or I would say if I call this as the ground is common to both the primary side and secondary side. It is true in any transformer which has only one single winding. It is as good as an inductance, nothing else basically, right? I hope you understand. It is as good as an inductance. And what you are looking at is self-induced EMF. And if you, yes, we do. So I should probably show two lines here. So it is a single core on which one single winding is wound. So if you look at it, the leakage will be really limited. There is no question of leakage in fact, because whatever links the primary has to link the secondary, right? Because you are going to have the same winding acting like primary as well as secondary. Yes. You are going to have essentially a core like this. Even when we were talking about this, we said that we are not going to wind the primary on one side and secondary on the other side. Instead, what you are going to do is, you are going to wind the whole thing and these two are going to be connected. So, the magnetic circuit is very much complete because the core is, in totality, if you look at it, it's a closed core. So, you are going to have essentially the entire magnetic field line passing like this, through this. It will just pass through this, like this, through the core. So I am looking at maybe a core type here. In core type construction, I am going to have the same winding wound on both the limbs, and they will be connected in series. Because they are connected in series, very clearly all the voltages across all the turns add up together. It is series addition. So the total voltage what I get will be the addition of all the voltages across each of the turns, right? So no isolation is one of the major problems of auto transformer. But one more problem I can say is, let us say I have a two winding transformer which is 220 volts by 220 volts. Let's say I take a 2-winding transformer which is having 220 volts and this is also 220 volts. I can connect these two in series and make it like an auto transformer to give me an output of 440 volts clearly. I may apply only 220 volts, but I can connect the two windings in series addition, then I will be getting 440 volts as the output. Maybe I need it for some particular application. Now, it is as good as connecting two transformers like this. So, this is 220 volts, this is another 220 volts. I am applying the supply here and I am taking the output here. I hope you understand. This is what is the equivalent. Now, if I say that this is my ground point, with respect to this, the potential at this point will be 440 volts. Clearly. Right? When I designed the transformer, I might have anticipated that I am going to apply a maximum of 220 volts. Nothing like, higher than that. Whether I look at the primary or secondary, both of them would have been rated for 220 volts only. Nothing more than that. Or 220 times root 2 at the most, because the peak of the voltage is root 2 times 220. But in this particular case, what is happening is, the voltage at this point happens to be at 440 volts. So the insulations can rupture if I continue to use it for too long a period, because it is facing the brunt of that 440 multiplied by root 2. That is the voltage that it is facing on a continuous basis. So I have to necessarily design the secondary if I know a priori that I am going to use this as an auto transformer. Then I should design the insulation of the secondary in such a way that it would be able to withstand 440 volts. Although originally when I conceived and I made the transformer, I was thinking it is going to be 220 volts. So unless I strengthen the insulation of the winding which is actually connected in series and away from the ground. Please note that this is away from the ground. So if I am connecting two windings in series and one of the windings is away from the ground, it is definitely going to bear the brunt of higher voltages. So I have to make sure that the insulation is strengthened. So I should say clearly the second problem that I may face is insulation rupture can happen. So I can have maybe insulation rupture as a potential problem in an auto transformer if I am trying to connect a two-winding transformer as an auto transformer. Yes. Let's try to look at it. That's what I'm going to come next. Okay? So let us try to probably look at one simple example of an auto transformer connection and see what kind of kVA rating I'm going to get, what kind of efficiency I'm going to get, and what kind of losses I'm going to incur in this particular case. Let me take maybe a little higher rated transformer, which is a 22 kVA transformer. Let me take maybe 2200 by 220 volts transformer. Okay? This is a two-winding transformer that I am talking about. But this is connected as an auto transformer. To derive, let me add these two voltages. How much is it? 2200 plus 220, 2420. 2420 volts from a 2.2 kV supply or mains. Okay? So I am trying to connect this using this auto transformer, rather two-winding transformer. I am trying to connect it as an auto transformer to derive this voltage. Right? Now, the question that is being asked is, without overloading any of the windings or any of the two windings, what is the maximum kVA that can be derived at the output? What is the maximum kVA that can be derived at the output? Okay? And one more thing, maybe that we'll have to specify is how much is the current flowing in each of the branches. During the maximum kVA output, specify the connection diagram and the currents drawn. That is another thing. Specify the connection diagram and the currents drawn. Fine? So let us try to take a look at this as to how this works. Hopefully this will clarify the concept about kVA rating. Right. So to start with, I am having 2200 volts on one side, and on the other side it is 220 volts. Okay? Now, if I am connecting full load, that means according to the kVA rating, this will have a current of 10 ampere and this will have a current of 100 amperes. That's what it is saying. Right? So, let me specify those currents as well. So, this is going to be 10 ampere, and if I connect a load here, whatever is the load value I can calculate definitely. This is going to be 100 amperes. And let's say maybe this is having N1 turns and this is N2 turns. 10:1. Right? Now what is being asked is, I have to connect two of them in series. This is the 2200 volts winding and that is the 220 volts winding. I am applying 2200 volts here. So this is 2.2 kV, and what I am getting here is 2.42 kV. Right? And I can't overload any of the winding. So I know for sure that this particular winding, which is the 220 volts winding, can carry a current of 100 amperes without getting overloaded. So I assume that it can carry up to 100 ampere. I will have to see how I am going to do the whole thing. So if this is carrying 100 ampere, hopefully this will essentially follow Kirchhoff's current law. So I will have 100 ampere here. So this will be returning again 100 ampere. Kirchhoff's current law. I am just showing KCL. That's it. Fine. What I am getting across the load is 2.42 kV and the current I have shown is 100 ampere. So how much is the total kVA rating? It is 2.42 multiplied by 10 power 3 multiplied by 100, that is 10 power 2. So I am going to have the kVA rating to be 2.42 multiplied by 10 power 5. Right? Look at the discrepancy in the rating. What I was having originally was 22 kVA. Now what I am having is 242 kVA. Right? It's such a large value that I am getting. This is because the turns ratio of the primary to secondary has become 1:10. So the voltage has become way too large on the secondary side because the primary and secondary voltages I have added. I have summed up the voltage and I am assuming that the load is going to get the entire thing. And after all, I am not overloading the secondary. So the secondary is able to supply 100 amperes of the current, same current, but the voltage has become 11 times whatever was the original voltage, what the transformer is meant to carry. right? Now, if this is 100 ampere, but I don't want the primary to carry beyond 10 ampere. It cannot carry more than 10 ampere. So let us say this is carrying some 10 ampere here. How do we decide the direction? Let us try to take a look. So the total current here is going to be 110 ampere. So clearly this will also be 110 ampere. Are you getting my point? Rather than supplying 10 ampere from the source, now I have ended up getting 110 amperes from the source. Because if I am saying that the output kVA is 2.42 into 10 power 5, it cannot come out of nowhere. It has to come from the source only, nothing else. So I have got the output kVA rating. I know the input voltage. I should be able to definitely get what is the input kVA that I have to supply. Input kVA has to be equal to output kVA by and large, except for whatever are the copper losses and constant losses. So input kVA and output kVA have to be equal to each other. Output kVA I have designed first. I have derived first. So input kVA has to be exactly same as this. So I should say input current, if I have to derive, input current has to be actually whatever is the output kVA divided by input voltage. Because I am assuming input kVA equal to output kVA. Right? So output kVA is 2.42 into 10 power 5. So that divided by 2200 will automatically give me what should have been the input current if I want this as my output kVA, which is same as input kVA. So this gives me 110 amperes directly. So 110 amperes I am supplying from the source. Mind you, the primary winding is still handling only 2.2 kV multiplied by 10 amperes. Nothing more than that. So it is handling only 22 kVA. Similarly, the output winding, the secondary winding is again handling only 220 volts multiplied by 100 amperes, which is again 22 kVA. So individually, if you look at the input and output windings, both of them are handling only 22 kVA each. So we are not overloading them. Only thing is, suddenly how come you are having so much of increase in the kVA? That is because they are conductively connected together. Are you getting my point? It is working now as a potential divider. So what you have done is essentially added the two voltages. So you have connected them in series. So if you look at the electromagnetic induction that is taking place, that is still fending for only 22 kVA. Nothing more than that. But if you look at actually what is happening in terms of the conductive coupling, one is electromagnetic induction coupling, the other one is or magnetic coupling, the other one is conductively how they are connected. They have been connected in such a way that you are essentially making the 220 volts look like it is put on the top of 2200 volts. So 2200 volts plus 220 volts together is supplying the load, and together it is giving you basically 2420 volts at 100 amperes itself, right? So I would be able to definitely multiply the capacity by a very, very large factor in the case of an auto transformer if I have primary to secondary turns ratio in the two winding transformer to be large. No doubt. But if I had designed this winding only to have 220 volts, it will not withstand say 2.2 kilovolts. The winding really had it. Completely the insulation will rupture in no time because you are trying to subject that to 2.4 kV, more than 2.4 kV. So you are going to see that especially the top portion of the winding will rupture right away. So auto transformer connections are extremely useful when I want to maybe slightly adjust the voltage. If I try to connect it somewhat like this, I am going to end up spoiling the transformer. This is theoretical. See, if I look at it, this was only designed for 220 volts. But this is my ground now. The ground is somewhere here. So with respect to ground, if I look at the voltage here, that is 2.4 kV, more than 2.4 kV. So when I actually design my insulation, I would design it only for 220 volts. But now I am applying 2.4 kV. So it may not be able to withstand it unless I had strengthened or reinforced the insulation, knowing that I am going to use it like this. So this will definitely result in rupture. Now, yeah. Between the two windings, that is two ends of the winding. But that is not going to matter, right? Because overall, what is the stress it is facing? It has to look at that. The overall stress it is facing is whatever is the voltage here with respect to the surrounding air or whatever. That is surrounding air. You are not going to do anything about it. Right? So, around that, all of them essentially work at ground potential. Hardly any potential. So, you would see that, the insulation is not able to withstand such a large voltage stress. Got it? Now, if I had originally said, yes, from the source. See, we are generally looking at the power grid as an ocean. Normally we say our power grid is an ocean. That's the reason if you are generating only 1 megawatt or 2 megawatt, you say that you are putting a drop in the ocean. So that's the reason we normally call the power source generally as infinite bus. We generally call this as infinite bus. The bus is a bus bar or a junction point. From the junction point, you probably derive so many load connections. So we call this as the infinite bus because we assume that its capacity is infinitely large, which is not really, clearly. But compared to 210 gigawatt, which is the overall generation capacity of our grid, 1 megawatt is less than a drop. No problem, right? So it is really an ocean. So you generally think, definitely this is not the case with respect to our lab. When we design our lab, we say normal capacity what we require is maybe 30 amperes, 50 amperes. Maybe if I have 20 tables like what we have in our electrical machines lab or ELL 100 lab, we say every particular table requires maybe 3 or 4, 5 ampere plug point we give. So 20 to 30 amperes, so 20 multiplied by 30. So we say this is what is the total amperage I require in this lab. It is not infinite. But we normally think that when we talk about the source, we talk about normally the power grid, the source from the power grid which has infinite capacity. So the inherent assumption is this 2.2 kilovolt source will be able to supply 110 amperes. That goes without saying. If definitely if it is only rated for 10 ampere, if I try to draw 110 amperes, whole thing will burn. No doubt. Right? So we normally go with the assumption of infinite bus. Right? Now, if this is 22 kVA and let's say the losses for this transformer, if I write P iron was maybe 200 watts and maybe P copper was 480 watts. For example, I am just arbitrarily taking some values again. Okay? I can definitely calculate the efficiency under unity power factor load condition under rated kVA when it is operating as a two-winding transformer. What will it be? It will be essentially 22,000 divided by 22,000 plus 200 plus 480. This will be the total efficiency that I would get for the two-winding transformer connection. when I am looking at the same thing as an auto transformer connection, the losses will not change. I hope you understand. We are still applying 2200 volts for the primary and I am having only 50 hertz. So the flux established is the same. And I am still drawing only 100 amperes of current from the secondary and 10 amperes I am supplying to the primary. So the copper losses will not change. But the output power has multiplied by a huge factor. Right? Because of which I am essentially going to see that if I calculate the efficiency now, it will be whatever is this 2.42 into 10 power 5 divided by 2.42 into 10 power 5 plus these two losses, that is 200 plus 480. Obviously the efficiency will be much better at unity power factor. So no wonder we say auto transformers have much less losses, much better efficiency. Right? So auto transformers definitely are very, very good when I have strengthened the insulation to a sufficient extent. If I have not done that, the transformer will be burnt. It will be very, very difficult for you to make the transformer withstand the summation of both the voltages. That will not be possible. Right? So, to summarize, auto transformers are good, especially when I want to regulate the voltages by a small fraction of the total voltage that I am applying. Typically, it is used in laboratory conditions very commonly for conducting tests on transformer, which you had done. Open circuit test and short circuit test you guys had done. And I showed you also that in the front end, you always connect an auto transformer. Right? So normally open circuit test or short circuit test, what you are going to do is to have an auto transformer, and from here you are going to connect maybe an ammeter, a voltmeter, a wattmeter, and then this will go to the transformer under test. This is how it is going to be. Right? If it is open circuit test, you will leave it open. If it is short circuit test, you are going to connect essentially the two terminals and short circuit it basically. So this is the auto transformer or variac. This also has another name called variac. Variac or auto transformer. And for some reason the industry people always say dimmer stat. So probably because the voltage can be decreased and a lamp's intensity can be reduced, dimmed. So maybe they use the word dimmer stat. So it's called dimmer stat as well. So these are the names for auto transformer. And here I will apply 220 volts single phase 50 hertz AC. Right? So the major applications of auto transformers are, one is voltage regulation. So I will be able to regulate the voltage to a particular value by connecting maybe a few turns extra, a few turns lower, whatever it is, I should be able to regulate the voltage. The second thing is, it is used for testing or conducting tests in laboratories, lab environment. The third one is, generally the three-phase auto transformers are very, very commonly used to start induction motors, which we will revisit when we are going to discuss induction motors. So these are used for starting three-phase induction motors. Right? So these are some of the applications of auto transformer. I would like you to do a little bit of self-study in this. How much of copper will be saved in an auto transformer, okay, compared to a two-winding transformer of similar rate. This you guys will study yourself. It is not given in PC Sen, it is given in Edward Hughes. Okay? How much of copper saving happens in an auto transformer as compared to a two-winding transformer of similar rate? So instead of using two windings, I'm going to use a single winding. Right? So how much of copper saving will happen when we have comparable ratings in both the cases? Right? So you guys will study that on your own, and it is not given in PC Sen. It is given in Edward Hughes Electrical Technology. It is given in any of the other machines books. If you possess any of them, you can definitely look at that. It's not a big deal. Okay? It is given in Electrical Technology by Edward Hughes. Let us try to work out maybe one problem. Yeah. You are talking about how to find whether 10 ampere is in this direction. The question was, so how do you find the current direction? 10 ampere, how do you know whether it is going from up to down or down to up? Basically, we had calculated the kVA. Once you calculate the kVA at the output, you know what is the input current from the voltage that is given. You have the voltage here. So because you have the voltage, from the voltage you should be able to get what is the kind of current you are anticipating. So the current what I am getting is 110 amperes. If this is 110 amperes and if 100 ampere is going in this direction, very clearly 10 ampere has to come downward. So that is the way you generally determine the direction. Okay, now we will try to work out one problem. So let me take my PET rating. Yes. See, it is very clearly given in the problem. I had given that we wanted to derive 2420 volts from 2200 volts. This can happen only if I add both the voltages. So this is series addition connection. You can also have, you could have had from 2200 volts, I want to get only 2000 volts or less, whatever. In which case, you could have just taken it from here itself. Or, if you don't have the tap, you can only have it in such a way that, in this case, we had gotten, this is, if I say this is minus, this is plus, this is minus, this is plus. So they are all in series addition. It's all AC. I'm talking about at this instant. Instantaneously. So they are coming in series addition. If I wanted less value than 2200, I could have actually, let us say the second winding is of 200 volts value, for example. In which case, 2200 minus 200 would have given me 2000. Right? So, I could have connected it in such a way that this is actually plus and this is minus. Because I would have the polarity of the transformer clearly marked, or I have to mark. That leads us to polarity test. Let me tell you that also. Polarity test, let me try to tell you. Little bit. So let us say I have a transformer like this. Right? I am applying V1 here. Okay? When I connect the voltmeter, right? I would measure whatever is the voltage V1 I am applying. Right? And if I try to connect the voltmeter here directly, I would have gotten V2. Let us say now I connect these two in series. I have connected them together. Two terminals I have connected together. And if I measure the voltage between these 2 points, between A and B, if I get the overall voltage as V1 plus V2, that means I have connected them in series addition. If I get rather V1 minus V2 or V2 minus V1, whichever is higher, that means I have connected them in series opposition. I hope you understand. I am connecting two sinusoids, but the two sinusoids can be aiding or they can be opposing. So whether I am connecting them in series addition or series subtraction depends upon when I measure the voltage after connecting these two terminals together. So let me say this is probably A1 and let me call this as B1. I have connected A1 and B1 together, and if I am getting the voltage to be V1 plus V2, I know that A1 and B1 when I connect together, they are in series addition. And if I had wanted 2420 volts in the previous problem what we discussed, I should have connected A1 and B1 together. Then I will get 2420 volt. Instead, if I had wanted 2200 minus 220, I should not connect A1 and B1 together. I should rather connect A1 to B, and I should have taken the voltage across A and B1. Then I would have had it as series opposition, which will actually give me 2200 minus 220. That's a wonderful question. I did give you there can be series addition and series subtraction. This brought out at least the series subtraction part. So I would be able to get by auto transformer connection either V1 or V2 alone, or I would be able to get V1 plus V2 or V1 minus V2. So I would be able to get all of them by having auto transformer connection. Got it? So is auto transformer clear? Any questions on this further? Yes? See, in a two-winding transformer being connected as an auto transformer, we are telling this. So if it is a two-winding transformer, I have four terminals. Which two terminals I want to connect together? That's what we were talking about. Two-winding transformer being converted into auto transformer. When I do that, which two terminals I have to connect if I want series addition? Which two terminals I have to connect if I want series opposition? This is what we were talking about. Is that clear? So finally when I connect the two terminals together, I have only two terminals coming out. Only A and B are coming out, or I will have A and B1 coming out. Finally. I will not have more than that. In the auto transformer here itself, let me say that maybe this is 2200 volts. Maybe this was 220 volts. Let me take this as 200 volts. That's fine. Okay? When I measured the voltage between A1 and A, this was 2200 volts. Whereas voltage between B1 and B at the same instant, I am talking about at the same instant if I am measuring, I am getting this as 220 volts. Fine. Now if I connect, this is A and A1, and along with A1 I am going to connect B1 and B, right? So maybe I am applying the voltage here as 200 volts, and if I try to look at the voltage here, this will be 2400 volts. Together. This is series addition. This is added because I am showing that B1 and A1 directly have the same kind of polarity, and when I am trying to connect them together, I am getting the total series addition. So when I am actually measuring, I am getting 2400 volts. If I had wanted 2000 volts, if I had at a particular instant, but later on during the negative half cycle you will have the same thing reversed. See, B is at a higher potential than B1, so if I call this as plus, this is minus. I should also call this as minus and this as plus. Only if I connect plus to minus, I'm going to have minus to plus, I'm going to have basically series addition, isn't it? See, I am essentially looking at this as minus, this as plus, and this as minus, and this as plus, right? So, if I am looking at it, this is actually, I am starting off with this as minus, this as plus, and this as plus, and this as minus. Unless I connect these two together, they will not be additive. That is, plus and minus, opposite polarities have to be connected together. Only then they will be in series addition. If I connect the same polarities together, it will be series subtraction. All of you guys know this, I suppose, right? If you have two battery, if I have plus, minus and plus, minus, if I connect it like this, it is series addition. Right? Have I marked the terminals differently? Maybe I should have said this is plus and minus are connected together. Okay. So I have shown it differently. That is the problem. I just realized that. So this has to be erased and I have to show it as though this is connected. Oh, this is connected here. Array, entire winding is gone. Okay. So this entire winding is gone, right? So I should show it as though this is connected here. Okay. That is where the problem lies. Thank you. Fine. Okay. Now if I want series subtraction, all I should have done is B I should put it here and B1 I should put it here. That's all. That will give me series opposition. Are you getting my point? Okay. So series addition and series opposition, I have to just invert. That's all. Got it? Can we proceed to the problem? So I am going to take my PET rating, which is 2.2 kVA. 2.2 kVA, 220 by 110 volts transform. Fine. Now, let me take maybe a open circuit test data and short circuit test data. Okay? I had done something because I didn't want you guys to calculate everything here. So, open circuit test data, I have taken this to be 110 volts, 0.8 ampere and 24 watts. Okay? And short circuit data, I have got 10 volts, 10 ampere and 48 watts. And this was done on the LV side and this was done on the HV side. Fine? So you would be able to calculate for this very clearly RC, XM, R1, R2 dash, X1, X2 dash. Assuming that R equivalent divided by 2 will be R1, R equivalent divided by 2 will be R2 dash also. Similarly, we will not be able to individually calculate for primary and secondary. So what we calculate as R equivalent, we will divide that by 2 and we will take that as R1 and R2 dash respectively. Got it? So, I think I will not calculate this. You guys will be able to calculate. I will only write the values. R1 and R2 dash, both of them we are getting as 0.24 ohm. Okay? And this is probably from the HV side. Right? And X1 equal to X2 dash, both of them I am getting as 0.77 by 2 approximately. This is also from HV side. And I am getting RC to be 509 ohms. This is from LV side. So if we are asking you to draw the equivalent circuit, you better transport everything to one side, either LV side or HV side. Okay, and XM is coming out to be 146 ohm. This is also from LV side. Fine. Now, the next question that is being asked is, calculate the efficiency at half load and unity power factor. Okay. So that you should be able to calculate as, if I am saying that the copper loss at half load will be 48 watts multiplied by half square, right? Because it is half the load, X square multiplied by full load copper loss. So that will be essentially 12 watts. So if it is unity power factor, I should be able to say this will be 2.2 kVA multiplied by half, that is what is the output, multiplied by unity power factor. This is the power factor. If the power factor had been 0.8, I should have put this 1 as, instead of that, 0.8. So divided by, again I should say 1100 plus 12 watts is the copper loss and P iron. P iron is already given as 24 watts. So this is what is P iron. Right? So this will give me efficiency at 50% load unity power factor. If I ask you to calculate, for example, the regulation at 50% load, 0.8 power factor, for example. So regulation at 50% load, 0.8 power factor, lag, for example. So if it is lagging power factor, I can say cos phi is 0.8 and sin phi correspondingly will be 0.6, because 0.8 square plus 0.6 square root is 1. If it had been 0.8 power factor lead, then I should say sin phi will be minus 0.6, because essentially the current direction would be not below voltage, it will be above voltage if it is leading. So correspondingly, sine and cos, you are going to have, cos will be still positive, sine will be the opposite sign of what you got for the other one, right? So using this, you should be able to say the current is only, this is HV side. So I am going to have 10 ampere as the I rated. So I will have 5 ampere as half I rated. So I should be able to write 5 multiplied by R equivalent cos phi plus X equivalent sin phi. That will be the voltage drop. That you have to divide it by rated voltage. Rated voltage is 220 if I am taking everything from high voltage side. So you guys should be able to calculate the regulation as well. Right? Okay? So please try to do a few more problems what is given in the tutorial sheet. That will probably give you more practice, and get back to me positively with your questions. Okay? Thank you.